So in the previous discussion session, we learned that the equations of motion for Dirac field, which was the Dirac's equations of motion, can be converted into a harmonic oscillator kind of equation of motion. Rather than a harmonic oscillator, we obtained the Klein-Gordon equation, this equation which we obtained originating from the Dirac equation of motion. What we did, we acted upon on the Dirac's equations of motion with minus iota times gamma mu del mu, and ultimately the Dirac equation therefore became the Klein-Gordon equation, which we know how to quantize courtesy the scalar fields quantization which we have learned in the previous sessions. In this case, only thing which we have is that this is not a real scalar field. First of all, it is a 4x1 column vector which comes with a 4 component thing, psi1, psi2, psi3, psi4. Remember, the psi here is a representative of a collection of a 4x1 vector which has 4 complex quantities at its disposal. Okay, so we have this structure which we obtain for Klein-Gordon equation. So now we want to know that the usual way of quantizing the scalar field. In the discussion session which we had done, we discussed about the quantization of the real scalar field, but anyway, a complex scalar field also can be quantized along the similar lines, which we have not done for in the discussion session, but you will see that it is not much different from the real scalar field. In the real scalar field, remember the coefficient of e to the power ikx and e to the power minus ik dot x were complex Hermitian conjugate of each other in order to get you a real phi. So this d3k gave rise to a real phi. For this and that to become Hermitian conjugate to each other, you will obtain a real phi. But suppose you drop the requirement of having a real phi, then there is no reason that these quantities and these quantities should be Hermitian conjugate to each other. In principle, I can put a different b of k over here and then get my business done. Initially, remember, we had started doing the business like that, and then we imposed the reality condition. So this time I'm talking about Dirac spinor, and which involves 4 of the fields. None of them are necessarily real. So I drop the demand that ak e to the power ikx and ak dagger e to the power minus ikx should be the structure of its Fourier domain. So let us go forward and try to see what kind of a structure we could impose, and therefore what do we learn from the standard quantization procedure. So okay, so we do first the usual quantization, and surprisingly or unfortunately for us, we will see that this usual quantization scheme, which was very well working for a harmonic oscillator structure and the scalar field, despite appealing, it leads us to some unphysical conclusions, which we will see, and therefore we have to tweak the usual quantization scheme in order to get a meaningful physics out. So let us see what is the unphysicality inherent in the usual quantization procedure. So again, we are looking for a solution of this equation first. Classically, I know these are the solutions. When we were discussing the Dirac equation of motion in the relativistic quantum mechanics domain, there also the same story emerged, that the particles are supposed to satisfy the Dirac equation and hence the Klein-Gordon equation as well. This time as well, we are the same structure. I know, despite it being a 4x1 dimensional vector, its space-time dependent part satisfies the same equation which a scalar field does, because all the derivatives are spatial derivatives or temporal derivatives. So therefore, its space-time dependence cannot be different from the space-time dependence of the scalar field. So therefore, the plane wave structure should be inherent in that as well. So I know the space-time dependency should be through e to the power I p dot x upon h bar minus iota energy plus minus, because energy comes in 2 signatures, plus or minus. This was true for even scalar field. So this E was not the energy, but let us say frequency. E upon h bar was the frequency, positive frequency and negative frequency, which was appearing even for scalar field. What is the total energy would be known from the Hamiltonian only in the quantum field theoretic picture. But plane wave structure comes with positive frequency and negative frequency, and e to the power ip dot x, e to the power minus ip dot x, both of them are captured by a generic p vector, because p vector can be positive or negative. So this is the solution of the Dirac equation. Okay. Now, so this part, which is the spinor part of this is the new feature which has arrived, because this is not a scalar field. Scalar field part was this much. Since it is not a scalar field, a new part in terms of a 4x1 dimensional column vector has appeared. And we know again, in order to satisfy the Dirac equation, this column vector has to maintain a particular structure. For instance, it could be coming with definite energy, positive or negative. So it has positive energy or positive frequency solution and negative frequency solutions. As well as we realized when we were discussing about the spinor structure that it has an extra degree of freedom or extra operator which quantifies that, which is the spin or the helicity of that. So either it can come with one helicity, spin half or spin minus half with the same energy, or spin half or spin minus half with the negative energy or frequency. So we list down both of them. So these two, this one and this one, are positive energy or positive frequency solutions. So minus E upon H bar appears in the exponential. So these are positive frequency solutions. Because if you work this I del del T, you will get a positive number out as eigenfunction. And the spinor part was, remember, was something called a phi naught and a chi naught, and there was a relation between phi naught and chi naught, which was related by sigma I pi summation over all the Pauli matrices and all the momentum components in the helicity operator, and divided by E plus mc square. So this was the structure. Go back to your Dirac equations note when we were trying to solve the Dirac equation. There, this solution emerged out. In order to satisfy the Dirac equation as well as the Klein-Gordon equation, phi naught and chi naught in the doublet phi naught and chi naught cannot be arbitrary. They have to be related like this. And further, if I demand that phi naught and chi naught individually have to be eigenfunctions for eigenstates for the helicity operator, it can come with 1010 or 0101. 1010 structure was for plus h bar by 2 helicity operator, and this one is minus h bar by 2, or call it loosely called the spin value, the spin half, the spin minus half, or as helicity Sz plus half, Sz minus half, with positive energy. For the negative energy, exponential comes with a wrong sign, plus E upon h bar t. This time it will also be plus E upon h bar t. This is plus h bar by 2 in the spin, and this is minus h bar by 2 in the spin. The factor which will changes in the denominator of these two things as well. E goes to minus E. So in the negative energy solution part, negative frequency solution part, you will get this E plus mc square or E minus E plus mc square, depending upon which sector you are talking about, positive frequency or negative frequency. So keep a note that while I am calling it positive energy, but just looking at the symbol E, energy ultimately will get decided by the Hamiltonian. This is field theory. So the parameter appearing over here is not been shown to be the eigenfunction of or the eigenvalue of the Hamiltonian operator. So I'm loosely calling it energy in the spirit of the Schrodinger equation structure, which we used to call it. Okay. So this is really positive frequency and negative frequency solutions which we are talking about. Okay. So therefore, if I go below, so I'm going to collect all the positive frequency solutions as symbol U. S will tell me about what spin value I'm going to talk about. A spin can take two values, plus half or minus half. Similarly, there are two negative frequency solutions, Vs plus half and V minus half. Their space-time dependence part are plane waves, one with plus iota Et and one with minus iota Et. So these are the four set of solution. Two in the spin half sector, positive energy, spin half and spin minus half, and two in the negative frequency sector, spin half and minus half. And in the spirit of harmonic oscillator structure with the solution, now I can write down all the possible mode function. Remember, these things do satisfy the Klein-Gordon equation upstairs. The Klein-Gordon equations have now four solutions: positive frequency solution, positive spin solution, positive frequency solution, negative spin solution, negative frequency solution, negative spin solution, and negative frequency solution, positive spin solution. So all these four are your mode functions. So these are the mode functions I'm going to write: positive frequency and negative frequency. And I'm going to associate operators just like harmonic oscillators mode function. Remember the same discussion. The mode functions of harmonic oscillators came with A and A dagger with U star. I had to add a dagger because I wanted the position operator to be Hermitian. This time I am not bounded to obtain that because the field which we are describing is not necessarily a real field. So in principle, I can write any other operator. So let me write it as a BS dagger. There is no relation a priori between A and B. There are 4 different operators for positive frequencies and different S, and similarly there are so there are 2 different operators for positive frequency with 2 different spins, and similarly for negative frequencies there are 2 different spins and 2 different operators. So overall I have a AP spin half, AP spin minus half, BP spin half, BP spin minus half. So this is the structure I have obtained. You can check that this is still a solution of a Klein-Gordon equation or the harmonic oscillator in the Fourier space. Okay, so far so good. I can obtain the psi dagger, which is Hermitian conjugate of this, by just taking the conjugate of this operator. So all this A will become dagger, B, which was already I had written in a dagger form, this will become just B. I had written it in the spirit of the harmonic oscillator. One thing comes with A and one thing comes with A dagger. You could have started with A and B as well, but just making connection more clear with the harmonic oscillator. If B becomes A, it becomes a real scalar field. So dagger structure I have put in by hand. There is no necessity that it has to be dagger over here and not the B itself. But if you make this choice, then your psi dagger becomes dagger here and no dagger here. And the cost that this USP, remember this USP is not a number now, it is a column vector, one of the column vectors, this or that, depending upon spin half, this is this column vector, or spin minus half, this is this column vector. So when I take the dagger, it will become a row vector. So therefore it is not a star but a dagger. So therefore I will get a USP dagger, and this thing was VSP, which becomes a dagger as well. So therefore I have a more robust or more mathematically rich structure for the Dirac field, because in addition to the oscillator operators, I have mode functions which are also vectors, row vectors or column vector, depending upon whether you are talking about psi or psi dagger. Okay, so now we know that psi and psi dagger which we have obtained are not just independent quantities anymore in the phase space, but iota times psi dagger is supposed to be the momenta conjugate to psi. So psi conjugate momenta is pi, which should be iota times psi dagger, and I know that the psi of x and pi of x prime should satisfy iota times delta of x minus x prime. So therefore there should be a non-trivial commutation relation between psi and psi dagger. So psi and psi dagger, so here should be a dagger, should therefore be delta functions up to a identity 4 cross 4. Why this identity 4 cross 4? Because all the times we are going to talk about this fields not as a collection of a single object operator, but a field coming with a structure commensurate with the 4 cross 1 vectors which are appearing in the mode functions as well. So therefore this is the structure which we are going to look for. Okay, so this will be ensured. So if I write my psi like this, and if I write my psi dagger like this, and I demand psi dagger should be delta function, and use the fact that d3p e to the power ip dot x minus x prime should be a delta function, should be a 2 pi cube times delta 3 of x minus x prime. So you see, when I write psi and psi dagger side by side, I will get 2 integrals, one from d3p from the psi and another d3p primed integral, let us say, from psi dagger. And collection of these 2 d3p should, at the end of the day, first it should get converted into a single integral over d3p, and then after the end of the day I should get a delta function out of it. You can see, maintaining what is the up and what is the up dagger, what you should get, and so on and so forth. You will see that it would be realized that this commutation relations between psi and psi dagger will be realized only when a and a daggers satisfy the usual commutation relation, that for different spin s and s dagger they should not be talking to each other. Spin number 1 has its own oscillator structure, spin number 2 has its own oscillator structure. So there are like 2 different oscillators. So one oscillator's A operator does not talk to another operator's A dagger, it talks to only itself. So first spin should be the same, and then the delta function should come about. If the spins are different, that means the oscillators are different, so they should not be commuting. They should not be non-commuting. They should be commuting rather. So spin delta function ensures that we are talking about the same. And similarly for space-time dependent P also, they should be the same. Otherwise, we are not talking about the same oscillator, and therefore the operators would commute. Okay. Similarly, different A's should also commute, depending whether or not P and P primed are same or not, and S primed are same or not. Two different A's are supposed to always commute. Two different A daggers are always supposed to commute. And the same story goes for the second set of oscillators of B. So B's are the oscillators with, let us say, negative frequency, but anyway, that is all right. And they have also the same structure in order to get the good commutation relations, and using the fact that the good commutation relation will come only from the converting the double integral over P into a single integral over P with this function in the hand. I should impose this kind of commutator structure on A and B, which is usual commutator relation between oscillators. So this is nothing mysterious. Only thing is that we started with an oscillator kind of equation. It has more than one component, therefore we are getting more than one operator set. But all of the sets are talking about oscillators, since psi talks about not one operator but really 8 operators. 8 operators in the sense of 4 complex entries. So therefore this set of operators are also different, and you will have this AS for plus half minus half, A dagger plus half minus half, BS plus half minus half, and BS dagger plus half minus half. So this is the structure which emerges out. This is mathematically slightly more rich, but nothing conceptually very different, apart from the fact that we are not talking about a real scalar field, but a complex oscillator kind of thing. Further, you need to impose, when you do this commutator kind of a structure, you will see that this USP and this USP dagger will hit each other. So these are vectors, co-vectors hitting each other, or column vector, row vector hitting each other. And therefore, we should know what happens when a column vector hits a row vector. So there should be, if I look for just the structure we had, this was the US set. The US set was here, and the VS set was over here. They both come with their individual normalization thing. I do not know how to normalize this vector here. I have not told how to normalize this vector here. Okay, so some normalization function should be there. It so happens it should be independent of spin. This is easy to verify that the spin half and spin minus half do not come with different normalization, and similarly for the negative frequency sector as well. But there is no a priori region that for negative frequency and positive frequency as well, you should have the same normalization. So I am maintaining one normalization in the positive frequency sector and another normalization in negative frequency sector. And in order to obtain this set of relation, there should be a good normalization which should be used. And that good normalization is also useful for getting a more clear story later on as well. So this is an exercise for you. What kind of N one should choose in order to get this along with this commutation relation, getting this commutator between psi and psi dagger. What should be the N? This should be fairly easy exercise. Impose this in your commutators and find out what are the N's and N primes. Okay, that would also become clear in a minute when we do another computation with US and VS. So now we have this relations in hand, we have commutator structure in hand. So let us go ahead and operate things on this. So first I will want to obtain this operator, which is all the spatial derivatives coming with a gamma factor acting on psi. Why do I need this operator? For that, let us go back to the Hamiltonian which we had obtained for the Dirac field. Remember, in the Dirac field's Hamiltonian derivation, the temporal derivative got exactly cancelled out, and we were left with only the spatial derivative with appropriate gamma i's multiplied to them. So you see, Hamiltonian is made up from, there is a gamma naught term in the first term and the second term both. So I can pull that out. So I would have a psi dagger and gamma naught, and I should have a minus I, gamma I, del I, and then m times psi. C is equal to 1 unit I'm using. So this operator's action on psi should be known in order to get the Hamiltonian. So that is what I'm going to do. I should be taking this operator, hitting it on the psi, and try to see what do I get. So when I take this and hit on the psi, there are gamma part, which is matrix, and the derivatives part, which are action on space-time. Space only, this is not time, this is spatial derivatives. So spatial derivatives are only in the e to the power ipx part, and the vector part of the matrix is only in the us. This is a column vector. So this operator and these operators together, they do not see anything else. They go right across the integration up to us. One part is behaving like vector to be hit upon by gamma i's, and one part is behaving like a function to be hit upon by delta xi. And similarly for the second part as well, the operator will go inside and hit that as well. Okay, so far so good, but there is another easier way, a convenient way of obtaining this action of this operator. You can do this exercise also. You can find out what happens after the end of the day. But an easier way is this: use the Dirac equation. I know the Dirac equation is I gamma mu del mu psi, not gamma I del I, which is required over here. So I write it like this. So therefore, I know the part which I am interested about is negative of minus iota gamma naught del naught psi. So that means the part I am interested over here is just this, I gamma naught del naught psi. So all this action of all this operator is equivalent to action of iota times gamma naught times the temporal derivative. So why not do that? Why to take this operator 3 derivatives and 3 matrix multiplication? Better 1 derivative and 1 matrix multiplication. So delta 0 will hit only the exponential part because the temporal dependence is only there. And if similarly in the second part also, the derivative will hit only the exponential part. This was a positive frequency thing, so it will give me a EP out. And this was a negative frequency thing, so it will give me a minus EP out. So there will be a sign. Minus sign will come between the two terms. Previously, there were no sign. They were added with a plus. After the derivative action, or equivalently after the action of this whole operator, I will get a negative sign in between. And a gamma 0, which I'm still to act. But wait, this is the structure, but I want to know the Hamiltonian. Hamiltonian involved, apart from the operator which we have obtained, another gamma naught should multiply the whole operator, and then a psi dagger should be multiplied, and d3x integration should be done. So that is what I'm aiming to do. I have obtained the action of this operator part, which is this. I will multiply a gamma naught to the whole thing. I will multiply a psi dagger to the whole thing, and I will do the d3x integral. So this is what I am supposed to do. And that will give rise to the Hamiltonian. So this operator, which gives rise to a negative sign difference between these two, times a d3p integrals, which is this, and the psi dagger, which is this, and this d3p integral, and gamma naught. When I multiply a gamma naught, you see in this term, both the terms we are having a gamma naught here and a gamma naught here. When I multiply a gamma naught, it becomes a gamma naught square, which is identity. So I get rid of gamma naught in the Hamiltonian immediately. All I am left to do is just multiply a psi dagger and take out the gamma naught. So the psi dagger multiplication will give me this and a 1 d3p integrals, and the action of this whole operator was this term with a sign difference with this d3p another integral, and at the end of the day I have to do the d3x integral to obtain the full Hamiltonian. Now you see the d3x integral will just see for the spatial dependency. Spatial dependency is coming only in the exponentials. Okay, and then you can use the fact you can have a spatial integrals of the exponential give rise to delta function, positive p plus p prime or p minus p prime, depending upon whether you combine this with this, you combine this with that, or this the second term with the first of the next term and the second term of the second of the next term. So you will get various combinations of exponential, and all of them doing the spatial integral will give rise to one of the delta functions. Use that, put it in the delta function and do one of the momentum integral. So delta function will get rid of one of the momentum integral, and then you will have just a simple combinations of AP multiplied to this, AP multiplied to that, BP multiplied to this, and BP multiplied to that. You will see the cross term will vanish under this. There will be no term which this A and B multiplied versus this and this multiplied. Once you make use of this Dirac delta functions integration, all this cross term will get cancelled. All it will survive will be this term surviving with this and this term surviving with that. So as a simple exercise, you will get this structure: AS dagger AS and BS dagger BS. S takes plus half minus half value, and P is the integral you will be left with. One of the integration of the momentum has been taken care by delta function, but you will be left with one of the integrations at the hand. Now let us stare at the Hamiltonian, what we have. The Hamiltonian, what we have is almost like the harmonic oscillator Hamiltonian, which this believed as a number operator, and this is the frequency they come up with. However, this time we have a collection of two set of oscillator, positive frequency and negative frequency. This is set of positive frequency. A's are the positive frequency operators and B's are the negative frequency operators. So they do come with positive frequency and negative frequency, and ultimately what is happening is that we are counting all the positive frequency oscillators and all the negative frequency oscillator and combining them with their frequency weightage to get the Hamiltonian. Compare with the structure which we had for scalar field. We had just AP dagger AP and a plus half of delta 0. That delta 0 has gone away, and this is being replaced by the negative frequency oscillators. But they are oscillators after all, because the spinor field has more set of fields inside. This is not one field but a collection of various fields. So therefore the Hamiltonian you are going to get is also collection of various oscillators. It so happens that some of the oscillators come with negative frequency, because we did not demand the hermiticity or anything for the field. The cost we have to pay is that you have to adopt the negative frequency. Remember, why did we not demand the hermiticity? Because we saw that they have to be complex numbers, they have to be operator in 4x1 space and so on. All these things, when we built our first order equations of motion story, there was inbuilt into that this can be realized only with the complex fields. It cannot be realized with the scalar fields, which are or the real quantities. So in order to have a first order equation, the cost you have to pay is to come up in the Hamiltonian with a negative frequency part. But they are oscillators and they do not talk to each other. Commutator between A and B's are zeros. So this is one set of oscillators and these are second set of oscillators. And we can assume that there is a ground state again, or the vacuum state, let us say, which is annihilated by both these. Ground state is annihilated. So this is like two oscillators. Joint ground state will be oscillator first ground state tensor, oscillator 2's ground state. And therefore this combined ground state will be annihilated by either of the operators. The same thing is happening here. The true ground state, which is ground state of all P's. So remember, in the scalar field part, the ground state was supposed to be ground state of all momentum vacuum. This time it has not only the momentum vacuum, this has spin vacuum as well as negative frequency vacuums. The full vacuum is vacuum for all oscillator of positive frequency side times vacuum of all negative frequency oscillators as well. So therefore the full vacuum will be annihilated by both A's and B's. But the story is problematic even after that. Though I have a vacuum state, now I can raise as many A's positive frequency things and as many B's negative frequency thing independently. There is no reason that A and B should be correlated. I can think of a different number operator in the positive frequency sector and different operator number excitation in the negative sector. This is like two oscillators ground state. I can have either 0 or 1, or I can have a 1 or 0. I can have a 2 here or a 0 here. Just like different P's oscillator structure did not command what other oscillators excitation should be. Similarly, positive frequency sector does not command what has to be excitation in the negative energy sector. How many particles I should keep in oscillators of one kind does not determine how many particles of those oscillators I should keep in the negative frequency side. So therefore, these are independent excitations. And therefore, there is a problematic possibility that I can excite the negative frequency particles more than the positive frequency particles, and I lead to a Hamiltonian which is negative. And if I keep on increasing the negative frequency oscillator sector more and more, I will get more and more negative Hamiltonian. And therefore, negative energy states, this Hamiltonian becomes unbounded from below, because in principle, I can excite infinitely many particles in the negative energy sector and no particle in the positive energy sector, positive frequency sector, or finite particles in positive frequency sector. End result will be Hamiltonian will become minus infinity. So at the end of the day, doing all the field theory, everything, I'm back to square one, where my Hamiltonian has become unbounded from below. So the all clever tricks which we played to convert things into operators in the hope of getting rid of negative frequency solutions does not pay off. It did quantization for scalar field wonderfully, but for spinor field, we are led to the same falsehood, same unphysicality which we were dealing with in the case of quantum mechanics. So quantum field theory has not helped us as far as spinor fields, spinor particles are concerned. How to handle this fact, whether these spinor things really exist or not, or there is something in which we can do in the quantization to save this story, will be discussed in the next class. But as of now, the message is the usual quantization does not work. The oscillator quantization does not work for these particles. These are some new particles. They are not behaving the same way scalar particles should have behaved. Okay, so we'll discuss more in the next discussion session. What should we do in order to save this, to not get the negative energy Hamiltonians? Okay, so I stop here.